Good day, everyone. I am Amira Beatriz, taking a Bachelor of Science in Material Science and Engineering. The paper that I will present you today is assessing the performance of thin film nanofiltration membrane with embedded Montmorillonites. This paper is under the supervision of Dr. Ruth Aquino. First is the introduction and objectives. The Earth is composed of nearly 70% water, 2.5% of fresh water, but only 1% is accessible to mankind. But due to overpopulation, industrialization, climate change, our freshwater ecosystem is continuously harmed. Thus, millions of people around the world suffer from water shortage. That is why it is desirable to develop a sustainable solution for water purification with low cost and energy consumption while minimizing the use of chemicals and its adverse effects on the environment. And this is where nanofiltration membrane comes in hand. Nanofiltration has the ability to separate multivalent from monovalent ions. It has a molecular weight cutoff of 100 to 2000 daltons and a pore size of 0.5 to 2 nanometers. This kind of membrane separation has been applied in water purification, seawater desalination, wastewater treatment, and many more. Aside from what is stated, it is also cheap, energy efficient, and does not have adverse effect on the environment. One way to fabricate nanofiltration membrane is interfacial polymerization. Interfacial polymerization is a technique for manufacturing commercial thin film composite membrane. Each layer can be optimized to attain desirable performance, and the reaction is fast and efficient. In IP, the reaction of diamine and acyl chloride forms a polyamide layer. However, one of the current problems of polyamide membrane is low efficiency and poor anti-fouling property. One of the additives that can be incorporated during IP are clays, such as sodium montmorillonite or NaMMT and organomontmorillonite or OMMT. NaMMT has a high thermal resistance, high mechanical property, and it has a hydrophilic silica layer. However, its dispersion in a polymer matrix is poor. NaMMT can actually be enhanced by intercalating a cationic surfactant within the layer, improving the material's hydrophilicity. After adding the surfactant, the NaMMT is now an organo-MMT, and its dispersion in the polymer matrix is now good. Objectives of the study: to prepare a modified membrane using MMT as an additive, compare the performance of NaMMT with organo-MMT in nanofiltration, and to optimize the best concentration for the organo-MMT. Next is the experimental. Using PSF as a support, 0.35 weight% of PIP in deionized water will be in contact with the support membrane surface for 2 minutes. After that, 0.2 weight% of trimethyl chloride and N-hexane along with the additives will be poured for 1 minute. This will then form a thin dense layer called the polyamide. The amine of the PIP will interact with the acyl chloride, forming the polyamide layer, which can either form a linear or cross-linked structure or even both. After that, cure the membrane in the oven for 10 minutes at 50 degrees Celsius and wash the membrane 3 times to remove the amine. Lastly, submerge the membrane in water bath until use. For the results and discussion, in the FTIR spectra of the additives, both NaMMT and OMMT has a peak at 3620 and 3675, which corresponds to the hydroxyl group, 990 for the siloxane, and 910 for the aluminum oxide hydroxide. However, only NaMMT had a peak at 3415, which was attributed to its bound water molecules. OMMT lacks this peak because of the hydrophobic alkane chains of the surfactant added. For the OMMT, a new peak at 2850 and 2915 can be seen, which is attributed to the long alkyl chains of DTA plus and 2988 for the amine group. For the crystallinity of the Montmorillonites, NaMMT has a basal spacing of 12.81 and 4.81, while OMMT has 3 basal spacings at 37.21, 18.07, and 12.01. This indicates that this additive is composed of paraffinic, mono, and biaryl layers, respectively. Comparing the two additives, when both are immersed in N-hexane, the spacing of OMMT enlarge at a greater degree compared to NAMMT. For the zeta potential of the Montmorillonites, NAMMT has a zeta potential of negative 24.07 millivolts because of the negativity that the aluminosilicates emit, while OMMT has a lower zeta potential of negative 7.6, which is due to the surfactant which neutralizes some of the aluminosilicates present. For the FTIR analysis of the membrane, a peak at 3,200 to 3,650 can be seen in all membranes due to the OH from PSF support and the COOH from the polyamide membrane. Comparing PSF to TFC and membranes with additive, an amide peak can be seen at 1,625. Upon the addition of Montmorillonites, a shift at 1030 can be seen due to the silicates from the NAMMT and the OMMT itself. In addition to the FTIR data, XPS was used to verify the embedment of the clay in the membrane. In the pristine membrane, only elements carbon, oxygen, nitrogen can be detected, but upon the addition of the additives, other elements such as calcium, sodium, silicon, iron, aluminum, magnesium, titanium, phosphorus, and potassium has been detected. This had confirmed the presence of the clay added. For the FE-SEM images of the membrane, comparing the surface morphology of polysulfone with TFC, it can be seen that polysulfone has a smoother surface as compared to TFC. The rough surface of the TFC can be attributed to the formation of the polyamide layer. For the modified membranes, it can be seen that the particles are embedded in the surface and that incorporating 0.058% of NAMMT to the membrane already forms agglomeration compared to 0.05% of OMMT. For the cross-sectional FE-SEM image, TFC membranes had a thickness of 116.11 nanometers, but upon the addition of the additives, the polyamide layer decreased because the MMT possibly prevented the TMC to react with PIP, therefore slowing down the reaction rate. For the wettability of the membrane, it can be seen that formation of the polyamide layer decreased the contact angle of the support layer from 58.98 to 33.23 degrees. Upon the addition of the additives, it can be seen that OMMT has the lowest contact angle compared to NAMMT. This confirms that adding surfactant to NAMMT improved the hydrophilicity of the clay. For the surface charge of the membrane, OMMT is more positive at pH 3 and less negative at pH 11 due to its positively charged surface. At pH 7, TFC is more negative due to the COOH that had deprotonated. This is the performance of the pristine membrane and membrane modified with NAMMT and OMMT. Comparing the pure water flux of the three, OMMT has the highest one with a flux of 53.15. Furthermore, the trend of the rejection is comparable to the trend from other studies. The rejection using 1000 ppm of salt showed that the highest salt rejection was obtained for Na2SO4 salts and the lowest is for MgCl2. This is because of the larger hydration radius of the magnesium. For the effect of OMMT concentration, from pristine membrane to 0.058% of NAMMT, the pure water flux of the membrane had increased from 37.98 to 53.15. But as the concentration of the additive further increases, the flux decreases. Thus, it can be said that the optimum amount of OMMT is 0.058% with a pure water flux of 53.15 and a salt rejection of 99.04%. For the anti-fouling property, for the pristine membrane, it showed a typical behavior where the flux is lower when the feed is PSA rather than pure water. For the membrane with OMMT, PSA with phosphate buffer registered a higher ionic strength, making it easier for the feed to pass through the membrane. Since there is a higher flux for the BSA feed, We examined the salt rejection of the TFN-OMMT membrane after the anti-fouling test, and it maintained a high salt rejection of 97.87%. TFN-OMMT has a molecular weight cutoff of 280 grams per mole, which agrees to the molecular weight cutoff of the NF membranes. For operating pressure, both membrane increased in flux as the pressure was increasing, but comparing the performance of TFC and TFN-OMMT, it can be seen that the modified membrane had a higher flux without sacrificing the rejection. For salt concentration, as the salt concentration of the feed increases, there was decrease in the flux for both membrane. This is because of the osmotic pressure of the feed increases. Once the osmotic pressure increases, the pressure required for the permeate to pass through also increases. For the feed pH, at high pH, the rejection decreases because the membrane is too negative, which causes the carboxyl group to repel from one another, making the pores bigger, resulting for salt to permeate the membrane. At low pH, the membrane is too positive, which makes the amine protonate, resulting to a very low rejection. For operating temperature, temperature feed usually affects the permeability and material property of the membrane. The flux of TFC and TFN membranes both have a comparable rejection, which indicates that OMMT enhances the water permeability without compromising the thermal resistance of the membrane. For the long-term test, even at 196 hours, the rejection is still 98.73%, which indicates that the membrane had a stable performance. So for conclusion, the embedment of OMMT on the polyamide layer enhanced the surface hydrophilicity of the membrane. The membrane with OMMT produced a better performance in terms of flux and salt rejection than NAMMT and the pristine membrane. 0.058% of OMMT is the optimum concentration for a thin film nanocomposite. And for that, thank you for your attention.